Welcome to example number 17, and in example number 17 they want you to find A, if it is, you have a 20-foot bar, it's a steel bar and it's 2.5 inches times 2.5 inches square and 20 feet long and has a temperature decrease, so your change in temperature equals, it's a decrease of 50 degrees Fahrenheit. Excuse me. And right now you're looking at it as just a free beam, or it's sitting there on the ground. Nothing's restricting the sides, and there's a temperature of a change of negative 50 degrees Fahrenheit. Let's put that up here. And then on top of that, you also do not have any loads into this. There's no P loads whatsoever. But you will have a change in, as long as you're not restraining it, you won't have any loads induced. And then B, the resulting stress is if you end up restraining these, the bar is going to want to pull in. So you will get a load on this beam or bar or whatever it is. So we're going to go ahead and start. Just sitting there on the side of the road, this 2-inch by 2-inch bar is sitting there. It's 20 foot long. You're asking me, okay, all of a sudden you get a cold spell coming, it drops negative 50 degrees. How much does it contract? And the equation you want to use, and this is for thermal expansion, which I'm surprised they're going over this, because in reality we typically don't consider this until you get larger structures. I think over 200 foot or 150 foot, even maybe up to 300 foot. The point is, we don't consider this in just a single span bridge. You typically will not look at the temperature forces unless you have something like the piers are really tall or something like that. Well, anyways, on to the equation here. You want to use is delta, and delta is your change in length, or elongation, however you want to say it, equals, let's see here, what's the equation? I always forget this. It is, I already put delta, equals N L T. And T equals, well, let's do this. Since I already called it temperature change is delta T, we'll do delta T. That's how I have always done it. He did a small t instead of a delta T. L is your original length, and N is the coefficient of thermal expansion, which is given. Those are just given to you. And this is given to you as N for steel, and it will always equal this, is 0.00. Let's see, 5 zeros, 3, 4, 5, and that's 6, 5. Concrete is 0.00060. And so it's pretty darn close. And it doesn't look like they put any units on this, but the units are actually, I don't know why they didn't include it, is inches per inch per degrees Fahrenheit. And of course, you don't have to understand what that means. It doesn't matter. Just know that, hey, that's what goes in there. And then when you look at the equation, you'll say, oh, well, does everything cancel out? These inches will cancel each other out. So you need to multiply it by degrees Fahrenheit, and then you will get what you want in your length. So putting everything into the equation, we get 4, 5 zeros. Times 20 foot. And I always put this in inches. Times 12 inches over foot. And then delta T is negative 50 degrees Fahrenheit. Let's put that into the calculator, and we get negative 0.078 inches. And that's pretty minimal, as you can see, for a 20 foot, and that makes about sense. That's what I would say. Okay, yeah, that's perfect sense. It only deforms 0.078 inches over 20 foot. So if you had 100 foot, it would be what? Times 5, 0.4 inches. And we've always said, I guess the conservative approach is an inch per 100 foot. So, but that's your answer for A. How much does it contract? It will get 0.078 inches shorter. Now let's move on to B. And B, I don't know if you understand what they're asking you to figure out, but you have two fixed. So either somebody's holding this beam or whatnot. Anyways, it's not going anywhere. And when that temperature drops, that beam is going to shorten. It's going to want to shorten. And since it can't shorten, it's going to want to go in. It can't shorten. It's going to pull away from the edges, and they want to figure out what is the resulting stress from that pull. And the way you have to look at it is, since we're assuming that it's not going to move, you effectively have a bar that wants to be this length but is being stretched to 20 foot. So you have a bar that's what, 20 foot minus, that's 19.02, let's say, 0.22 feet, and you're stretching it. So you want to go, and this isn't the easiest thing to think of. So you have a bar that's 19.922 feet, and you want to stretch it to 20 foot. So when you stretch it, the deflection equals, well, we already got it. It's negative 0.078. And you want to look at it as a deflection equals PL over AE equation. So you have negative, positive, it doesn't matter. We're just going to say 0.0078 inches. We're solving for P. Actually, what were we solving for? It says the stress. So we want to find the P, and then we want to divide it by the inches squared. And the L, we know, is 20 foot. 20 foot times 12 inches over feet to get it to inches. We're actually going to solve for PL, or in P over A, which, if you remember, is stress. There's P over A, which is also stress. Then E is, since this is steel, it is, once again, 29 million PSI. And let's run that through the equation. Let's solve for F, or stress, which is also P over A. Let's solve for P over A. So P over A equals, well, you want to divide by that and multiply by 29 million. So you have 0.078 inches. And you're multiplying it by 29 million. Get it to the other side, PSI. And then you're going to divide by 20 foot times 12 inches per foot. And then we get P over A also equals stress, tensile stress. So when we get the calculator, 0.078 inches times 29, 1, 2, 3, 4, 5, 6 zeros, divided by 20, divided by 12, equals 9,245. And that should be PSI. And let's check the units over here. This is PSI times inches divided by inches equals PSI. And let's double check this. He has 9,425 PSI. I have 9,245. And actually, I'm wrong. I just got it off my calculator incorrectly. It actually is 9,425 PSI. And that matches what he got. And that is your answer. And hopefully that makes sense to you. It's not as easy as the A problem. It takes a little bit of self-thought of, okay, well, the new beam is 19.922 feet, but we're restricting it, and we're actually restricting it at the 20 feet, so it's actually a 19.92 feet bar stretched to 20 foot, sorry. And that is a deformation of 0.078 inches. So you have to figure out what your load is and your area is, which also equals stress. P over A equals stress. So that is the answer.